in atomic, molecular, and optical physics and quantum chemistry. The molecular Hamiltonian is the Hamiltonian operator representing the energy of the electrons and nuclei in a molecule. This operator and the associated Schrödinger equation play a central role in computational chemistry and physics for computing properties of molecules and aggregates of molecules, such as thermal conductivity, specific heat, electrical conductivity, optical and magnetic properties, and reactivity. The elementary parts of a molecule are the nuclei, characterized by their atomic numbers, Z, and the electrons, which have negative elementary charge, -e. Their interaction gives a nuclear charge of Z plus Q, where Q equals -n, with n equal to the number of electrons. Electrons and nuclei are, to a very good approximation, point charges and point masses. The molecular Hamiltonian is a sum of several terms. Its major terms are the kinetic energies of the electrons and the Coulomb interactions between the two kinds of charged particles. The Hamiltonian that contains only the kinetic energies of electrons and nuclei, and the Coulomb interactions between them, is known as the Coulomb Hamiltonian. From it are missing a number of small terms, most of which are due to electronic and nuclear spin. Although it is generally assumed that the solution of the time-independent Schrödinger equation associated with the Coulomb Hamiltonian will predict most properties of the molecule, including its shape, calculations based on the full Coulomb Hamiltonian are very rare. The main reason is that its Schrödinger equation is very difficult to solve. Applications are restricted to small systems like the hydrogen molecule. Almost all calculations of molecular wave functions are based on the separation of the Coulomb Hamiltonian first devised by Born and Oppenheimer. The nuclear kinetic energy terms are omitted from the Coulomb Hamiltonian, and one considers the remaining Hamiltonian as a Hamiltonian of electrons only. The stationary nuclei enter the problem only as generators of an electric potential in which the electrons move in a quantum mechanical way. Within this framework, the molecular Hamiltonian has been simplified to the so-called clamped nucleus Hamiltonian, also called electronic Hamiltonian, that acts only on functions of the electronic coordinates. Once the Schrödinger equation of the clamped nucleus Hamiltonian has been solved for a sufficient number of constellations of the nuclei, an appropriate eigenvalue can be seen as a function of the nuclear coordinates, which leads to a potential energy surface. In practical calculations, the surface is usually fitted in terms of some analytic functions. In the second step of the Born-Oppenheimer approximation, the part of the full Coulomb Hamiltonian that depends on the electrons is replaced by the potential energy surface. This converts the total molecular Hamiltonian into another Hamiltonian that acts only on the nuclear coordinates. In the case of a breakdown of the Born-Oppenheimer approximation, which occurs when energies of different electronic states are close, the neighboring potential energy surfaces are needed. See this article for more details on this. The nuclear motion Schrödinger equation can be solved in a space-fixed frame, but then the translational and rotational energies are not accounted for. Only the atomic vibrations enter the problem. Further, for molecules larger than triatomic ones, it is quite common to introduce the harmonic approximation, which approximates the potential energy surface as a quadratic function of the atomic displacements. This gives the harmonic nuclear motion Hamiltonian. Making the harmonic approximation, we can convert the Hamiltonian into a sum of uncoupled one-dimensional harmonic oscillator Hamiltonians. The one-dimensional harmonic oscillator is one of the few systems that allows an exact solution of the Schrödinger equation. Alternatively, the nuclear motion Schrödinger equation can be solved in a special frame that rotates and translates with the molecule. Formulated with respect to this body-fixed frame, the Hamiltonian accounts for rotation, translation and vibration of the nuclei. since Watson introduced in 1968 an important simplification to this Hamiltonian. It is often referred to as Watson's nuclear motion Hamiltonian, but it is also known as the Eckert Hamiltonian, Coulomb Hamiltonian. The algebraic form of many observables, i.e., Hermitian operators representing observable quantities, is obtained by the following quantization rules. Write the classical form of the observable in Hamilton form. Both vectors are expressed with respect to an arbitrary inertial frame, usually referred to as laboratory frame or space-fixed frame. Replace P by and interpret Q as a multiplicative operator. Here is the Nabla operator, a vector operator consisting of first derivatives. The well-known commutation relations for the P and Q operators follow directly from the differentiation rules. Classically, the electrons and nuclei in a molecule have kinetic energy of the form P2, and interact via Coulomb interactions, which are inversely proportional to the distance Rij between particle I and J. In this expression ρ stands for the coordinate vector of any particle, but from here on we will reserve capital R to represent the nuclear coordinate, and lowercase r for the electrons of the system. The coordinates can be taken to be expressed with respect to any Cartesian frame centered anywhere in space, because distance, being an inner product, is invariant under rotation of the frame in, being the norm of a difference vector. Distance is invariant under translation of the frame as well. By quantizing the classical energy in Hamilton form, one obtains the molecular Hamilton operator that is often referred to as the Coulomb Hamiltonian. This Hamiltonian is a sum of 5 terms. They are the kinetic energy operators for each nucleus in the system, the kinetic energy operators for each electron in the system, the potential energy between the electrons and nuclei, the total electron-nucleus Coulombic attraction in the system, the potential energy arising from Coulombic electron-electron repulsions, the potential energy arising from Coulombic nuclei-nuclei repulsions, also known as the nuclear repulsion energy. See electric potential for more details. Here m is the mass of nucleus I, Z is the atomic number of nucleus I, and m is the mass of the electron. The Laplace operator of particle I is, since the kinetic energy operator is an inner product, it is invariant under rotation of the Cartesian frame with respect to which xi, y, and z are expressed. Small terms. In the 1920s, much spectroscopic evidence made it clear that the Coulomb Hamiltonian is missing certain terms, especially for molecules containing heavier atoms. These terms, although much smaller than kinetic and Coulomb energies, are non-negligible. These spectroscopic observations led to the introduction of a new degree of freedom for electrons and nuclei, namely spin. This empirical concept was given a theoretical basis by Paul Dirac when he introduced a relativistically correct form of the one-particle Schrödinger equation. The Dirac equation predicts that spin and spatial motion of a particle interact via spin-orbit coupling. In analogy spin other orbit coupling was introduced. The fact that particle spin has some of the characteristics of a magnetic dipole led to spin-spin coupling. Further terms without a classical counterpart are the Fermi contact term, and nuclear quadrupole coupling. Finally, a parity-violating term predicted by the Standard Model must be mentioned. Although it is an extremely small interaction, it has attracted a fair amount of attention in the scientific literature because it gives different energies for the enantiomers in chiral molecules. The remaining part of this article will ignore spin terms and consider the solution of the eigenvalue equation of the Coulomb Hamiltonian, the Schrödinger equation of the Coulomb Hamiltonian. The Coulomb Hamiltonian has a continuous spectrum due to the center of mass motion of the molecule in homogeneous space. In classical mechanics, it is easy to separate off the COM motion of a system of point masses. Classically, the motion of the COM is uncoupled from the other motions. The Coulomb moves uniformly through space as if it were a point particle with mass equal to the sum mtot of the masses of all the particles. The kinetic energy of this particle can take any positive value. The position of the Coulomb is uniformly probable everywhere, in agreement with the Heisenberg uncertainty principle. By introducing the coordinate vector x of the center of mass as 3 of the degrees of freedom of the system and eliminating the coordinate vector of one particle, so that the number of degrees of freedom stays the same, one obtains by a linear transformation a new set of coordinates t. These coordinates are linear combinations of the old coordinates of all particles. By applying the chain rule, one can show that the first term of is the kinetic energy of the Coulomb motion, which can be treated separately since does not depend on x. As just stated, its eigenstates are plane waves. The potential V consists of the Coulomb terms expressed in the new coordinates. The first term of has the usual appearance of a kinetic energy operator. The second term is known as the mass polarization term. The translationally invariant Hamiltonian can be shown to be self-adjoint and to be bounded from below. That is, its lowest eigenvalue is real and finite, although is necessarily invariant under permutations of identical particles. Its invariance is not manifest. Not many actual molecular applications of exist. See, however, the seminal work on the hydrogen molecule for an early application. In the great majority of computations of molecular wave functions, the electronic problem is solved with the clamped nucleus Hamiltonian arising in the first step of the Born-Oppenheimer approximation. See ref. For a thorough discussion of the mathematical properties of the Coulomb Hamiltonian. Also, it is discussed in this paper whether one can arrive a priori at the concept of a molecule from the properties of the Coulomb Hamiltonian alone. Clamped nucleus Hamiltonian. The clamped nucleus Hamiltonian describes the energy of the electrons in the electrostatic field of the nuclei, where the nuclei are assumed to be stationary with respect to an inertial frame. The form of the electronic Hamiltonian is the coordinates of electrons and nuclei are expressed with respect to a frame that moves with the nuclei, so that the nuclei are at rest with respect to this frame. The frame stays parallel to a space-fixed frame. It is an inertial frame because the nuclei are assumed not to be accelerated by external forces or torques. The origin of the frame is arbitrary. It is usually positioned on a central nucleus or in the nuclear center of mass. Sometimes it is stated that the nuclei are at rest in a space-fixed frame. This statement implies that the nuclei are viewed as classical particles, because a quantum mechanical particle cannot be at rest. Since the nuclear positions are constants, the electronic kinetic energy operator is invariant under translation over any nuclear vector. The Coulomb potential, depending on difference vectors, is invariant as well. In the description of atomic orbitals and the computation of integrals over atomic orbitals, this invariance is used by equipping all atoms in the molecule with their own localized frames parallel to the space-fixed frame. As explained in the article on the Born-Oppenheimer approximation, a sufficient number of solutions of the Schrödinger equation leads to a potential energy surface. It is assumed that the functional dependence of E on its coordinates is such that for where t and s are arbitrary vectors and delta phi is an infinitesimal angle, delta phi greater than delta phi 2. This invariance condition on the pairs is automatically fulfilled when the pairs is expressed in terms of differences of and angles between the re, which is usually the case. Harmonic nuclear motion Hamiltonian. In the remaining part of this article we assume that the molecule is semi-rigid. One would like to recognize in its solution the motion of the nuclear center of mass, the overall rotation of the molecule, and the nuclear vibrations. In general, this is not possible with the given nuclear kinetic energy, because it does not separate explicitly the 6 external degrees of freedom from the 3n-6 internal degrees of freedom. In fact, the kinetic energy operator here is defined with respect to a space-fixed frame. If we were to move the origin of the SF frame to the nuclear center of mass, then, by application of the chain rule, nuclear mass polarization terms would appear. It is customary to ignore these terms altogether, and we will follow this custom. In order to achieve a separation, we must distinguish internal and external coordinates, to which end Eckert introduced conditions to be satisfied by the coordinates. We will show how these conditions arise in a natural way from a harmonic analysis in mass-weighted Cartesian coordinates. In order to simplify the expression for the kinetic energy, we introduce mass-weighted displacement coordinates. Since the kinetic energy operator becomes, if we make a Taylor expansion of V around the equilibrium geometry, and truncates after 3 terms, we can describe V with only the third term. The term V0 can be absorbed in the energy. The second term is vanishing because of the equilibrium condition. The remaining term contains the Hessian matrix F of E, which is symmetric and may be diagonalized with an orthogonal 3n times 3n matrix with constant elements. It can be shown from the invariance of V under rotation and translation that 6 of the eigenvectors of F have eigenvalue 0. They span the external space. The first 3n-6 rows of Q are, for molecules in their ground state, eigenvectors with non-zero eigenvalue. They are the internal coordinates and form an orthonormal basis for a dimensional subspace of the nuclear configuration space R3n. The internal space. The zero-frequency eigenvectors are orthogonal to the eigenvectors of non-zero frequency. It can be shown that these orthogonalities are in fact the Eckert conditions. The kinetic energy expressed in the internal coordinates is the internal kinetic energy. With the introduction of normal coordinates, the vibrational part of the Hamiltonian for the nuclear motion becomes in the harmonic approximation. The corresponding Schrödinger equation is easily solved. It factorizes into 3n-6 equations for one-dimensional harmonic oscillators. The main effort in this approximate solution of the nuclear motion Schrödinger equation is the computation of the Hessian F of V and its diagonalization. This approximation to the nuclear motion problem, described in 3n mass-weighted Cartesian coordinates, became standard in quantum chemistry. Since the days that algorithms for accurate computations of the Hessian F became available. Apart from the harmonic approximation, it has as a further deficiency that the external motions of the molecule are not accounted for. They are accounted for in a row vibrational Hamiltonian that sometimes is called Watson's Hamiltonian.